Welcome to this deep dive. Today, we're jumping into one of the hottest areas in AI right now, generative models.
Yeah, absolutely. And specifically, those large language models, the LLMs that you're seeing everywhere.
Exactly. We're moving beyond AI that just, identifies things. These models are actually creating brand new data.
That's the key shift, isn't it? Not just analyzing, but synthesizing. Think hyper-realistic images or text that sounds completely human.
Right. Instead of just spotting a cat, it's drawing a new one or writing an email.
Precisely. From analysis to creation.
And our source for this deep dive is this really solid guide. It kind of walks you through everything from the fundamentals of deep learning right up to these state-of-the-art models.
Yeah, it's quite comprehensive. So our mission for you today is to really pull out the crucial bits, the technical nuggets you need.
We want to give you that core understanding, right? So you know how these powerful systems actually tick, what they can do, maybe what they can't do yet.
It's like a shortcut to getting properly informed on something that's, well, pretty important now.
Okay, so the plan is build it up. Start with the basics, the engine room neural networks.
How they learn?
Then look at the early attempts at generation, like autoencoders and GANs,
The pioneers.
which leads us to the big one, the transformer architecture.
The game changer.
And that powers the giants. We hear about GPT, BERT, T5, Claude, Mistral.
We'll unpack those.
And then wrap up with some practical advice, like if you actually wanted to use one of these, what do you need to think about?
Sounds like a plan.
Okay, let's get started then. That absolute foundation. What is the core tech making all this generation happen?
Right. So at the heart of it all, it's deep learning, and specifically neural networks.
Loosely based on the brain, I always hear.
Yeah, that's the inspiration. Think of them as these networks of interconnected nodes or neurons arranged in layers.
Okay, so you've got an input layer.
Exactly. That takes in the raw data pixels from an image, maybe numbers representing words.
And then it goes through hidden layers.
Correct. Multiple hidden layers. And this is where the real computation happens. Each neuron takes inputs, does some math, basically a weighted sum, and applies a nonlinear function.
And making them deep means stacking lots of these layers.
Precisely. And that's key for generation, because having many layers lets the network learn really complex hierarchical patterns. It builds up understanding step by step.
Like seeing edges, then shapes, then whole objects, or words, then phrases, then sentences.
You got it. It learns these intricate relationships directly from the data, which brings us to training.
Right. How does it actually learn? What's going on under the hood?
Okay, so think of it as guided trial and error. You showed an example, it makes a prediction that's the forward pass. Data flows through, you get an output.
Which is probably wrong at the start.
Almost certainly. So you need a way to measure how wrong. That's the loss function. It's just math that compares the network's output to the right answer.
Okay, so you know it messed up. How does it fix itself?
That's the clever bit. The backward pass, or backpropagation. It uses calculus gradients, the chain rule, basically, to figure out how much each connection, each weight and bias in the network contributed to that error.
Okay, so it knows who to blame.
Sort of, yeah. And crucially, it knows how to adjust them, nudge them up or down to reduce that error next time. An optimizer algorithm, like Atom, handles those adjustments efficiently.
And it just keeps doing this. Forward, measure error, backward, adjust.
Go over and over, usually with small batches of data at a time. Going through the entire data set once is called an epoch, and training involves many, many epochs.
Gotcha. And you mentioned deep layers. What about wide? More neurons in a layer.
Exactly. Deep helps learn complex hierarchies. Wide gives each layer more capacity to learn different features at that level.
So for someone listening, thinking about these systems, what's the core takeaway here?
I think the main insight is this combination. The layered structure lets it represent complexity, and the training process lets it learn those complex patterns from vast amounts of data. That learned internal knowledge is what makes generation possible.
But it comes at a cost, right?
Oh, definitely.
Yeah.
Huge data needs, massive computational power. And you're always balancing model size, more power, but maybe slower, needs more data, risks overfitting.
Overfitting, just memorizing the training data.
Yeah, instead of learning general patterns. So you balance size against efficiency and generalization. It's a constant design challenge if you're building these things.
Okay, so we have this powerful learning machine. How did people first get them to, create new things, not just classify?
Right. Well, two really influential early approaches were autoencoders and generative adversarial networks, GANs. Very different ideas.
Autoencoders.
Yeah.
Sounds like compressing data.
That's a good way to put it. A basic autoencoder learns to squash input data down into a smaller, sort of compressed representation, the latent code, and then it learns to reconstruct the original data from that code.
So an encoder shrinks it. A decoder expands it back.
Exactly. And the goal is just to make the reconstructed output as close to the original input as possible. By doing that, it has to learn a really efficient way to represent the data in that smaller, latent space.
What's the use case there?
Standard autoencoders are good for things like dimensionality reduction smart compression, or denoising, learning to ignore the noise and reconstruct the clean signal, finding useful features in data.
Okay, but how does that generate something totally new?
For that, you need a twist. Variational autoencoders, or VAEs. They add probability into the mix.
How so?
Instead of the encoder mapping an input to one single point in that latent space, it maps it to a whole distribution, usually like a fuzzy cloud, a Gaussian, defined by a mean and variance.
Okay. Why the fuzziness? What does that achieve?
That's the key. It forces the latent space to be smooth and continuous. Points near each other in the latent space correspond to outputs that are similar.
So you can explore that space.
Precisely. To generate something new, you don't need an input. You just pick a random point from a simple distribution, like a standard bell curve, feed that point into the decoder, and it generates a plausible output.
And because the space is smooth.
Sampling nearby points gives you variations of the same kind of thing. You can even pick 2 points in the latent space, draw a line between them, sample along that line, and see the output smoothly morph from one thing to another.
Cool. So VAEs, stable, easy to sample from?
Generally, yes. They're pretty well behaved during training. The main drawback people mention is that the samples can sometimes look a bit blurry or less sharp compared to GANs.
Right, the joint. This is where it gets kind of wild, right? The competing networks.
Exactly. Generative Adversarial Networks. This was a brilliant idea. You have 2 networks, a generator and a discriminator, locked in a competition.
Okay, lay out the game.
The generator's job is to create fake data, say, images that look totally real. It starts from just random noise.
And the discriminator.
The discriminator is the critic. Its job is to look at an image and decide, is this real from the actual training data set, or is it fake, made by the generator?
And they train together, pushing each other.
Yes, that's the adversarial part. The generator tries to get better at fooling the discriminator. The discriminator tries to get better at spotting the fakes. They constantly adapt to each other.
So the generator's forced to get really, really good.
Incredibly good. This constant pressure drives it to produce outputs that are often stunningly realistic, very sharp. That's why GANs became famous for generating high-fidelity images.
What are the catches? You mentioned VAEs can be blurry. What about GANs?
Training them can be a real headache. It's like balancing a knife edge. If the discriminator gets too good too fast, the generator can't learn. If the generator fools the discriminator easily, it might not improve much.
Unstable.
Can be, yeah. And they can suffer from mode collapse.
Don't collapse.
Where the generator finds one, or just a few types of outputs that consistently fool the discriminator, and it just keeps producing those, ignoring the diversity of the real data, like only generating pictures of tabby cats when the data set has all kinds of cats.
Oh, okay. So engineers have tricks for that.
Oh, yeah. Lots of research went into stabilizing GAN training, different network architectures, loss functions like Wasserstein GANs, WGNs, using specific evaluation metrics like FID to track progress. And you get cool variants like StyleGAN, where you can actually control attributes of the generated image.
Okay, so autoencoders and GANs were big milestones. But then came the transformer. That really shifted things, especially for text, didn't it?
Oh, massively. The transformer architecture from that attention is all you need paper, it just changed the whole paradigm for sequence data. It broke away from processing things step by step.
How did it do that? What was the magic ingredient?
The core mechanism is self-attention. Instead of looking at words one by one like older models did, self-attention lets every word in a sentence look at every other word in that same sentence all at the same time.
All at once.
Yeah, to figure out the context. Which words are most relevant to this specific word's meaning in this specific sentence?
Can you give an analogy?
Sure. Imagine you're reading a really dense sentence. For each word, your brain kind of highlights the other words that are most important for understanding that word's role. Attention does something similar mathematically.
Ow.
It calculates these attention scores between pairs of words. High score means pay close attention to this other word. It uses these things called query, key, and value vectors derived from each word's representation to compute these scores.
And this helps with long sentences, like understanding connections between words far apart.
Exactly. That's a huge advantage. It captures long-range dependencies much more effectively than older recurrent models, which could sometimes forget earlier parts of a sequence.
And you said it does this all at once. Does that mean it's faster?
That's the other massive win. The attention calculations for all word pairs can happen in parallel. They don't depend on each other sequentially.
Ah, perfect for modern hardware like GPUs.
Totally. This parallelizability is a key reason transformers can be trained on such enormous data sets much more quickly than previous architectures. They also use something called multi-head attention.
Which is?
Basically, doing the attention calculation multiple times in parallel, each time looking for different kinds of relationships, like having multiple sets of eyes scanning the sentence for different connections simultaneously.
So a transformer model is built by stacking these attention layers.
Yeah, the basic building block is a transformer block. It usually has a multi-head self-attention layer, followed by a simpler feed-forward network, and they stack these blocks up. They also use important tricks like residual connections and layer normalization to help train really deep stacks of these blocks without the training going haywire.
One thing, though, if attention looks everywhere at once, how does it know the order of the words? Dog bites man versus man bites dog.
Great question. Because, yeah, attention itself doesn't care about order. So they add something extra. Positional encodings. These are basically little signals added to each word's input representation that tell the model the word's position in the sequence, first word, second word, etc. So yeah, understanding attention is fundamental. It's the engine driving pretty much all the large models we hear about today, not just for text, but increasingly for images, audio, you name it. And as the source notes, the key variations for LLMs are encoder-only, decoder-only, or the full encoder-decoder stack.
Which brings us neatly to the giants, the large language models, LLMs. So take that transformer, make it huge, train it on basically the internet.
Pretty much. LLMs are transformer models scaled up dramatically, pre-trained on absolutely massive amounts of text and code. And yeah, we can group the big ones by which part of the transformer architecture they mainly use.
Okay, let's start with the one everyone knows, GPT.
Right. GPT generative pre-trained transformer. That's the classic decoder-only model. Its whole training goal is super simple but powerful. Predict the next word, or more accurately, the next token, given all the previous tokens.
And it uses that causal mask you mentioned, only looking backwards.
Exactly. The causal mask means when it's predicting the next token, it can only attend to the tokens that came before it. This structure makes it inherently good at generating text sequentially, one token after another.
Which makes sense for, well, generating text.
Perfectly suited for it. And the scale they achieved, like GPT-3, GPT-4, it blew people away with its few-shot learning, meaning you could give it a task description and maybe just a couple of examples in the prompt, and it could often perform that task surprisingly well without needing any specific retraining or fine-tuning.
Okay, so if I'm building something, when do I reach for a GPT-style model?
Think generation. Writing assistants, drafting emails, articles, creative writing, code generation, chatbots, conversational AI, that's its sweet spot.
Strengths and weaknesses.
Strengths: incredible fluency, great at adapting to tasks via prompts. Weaknesses: can hallucinate, make stuff up convincingly, and the really big ones are computationally expensive to run.
All right, so if GPT's decoder is for generation, what about BERT?
BERT, bidirectional encoder representations from transformers. That's the classic encoder-only model. Its purpose isn't generation, it's deep understanding of text.
Bidirectional, so it looks both ways.
Exactly. Unlike GPT's causal mask, BERT's attention can look at the entire input sequence both before and after a given token to understand its context fully.
How's it trained for understanding?
The key training task is masked language modeling, or MLM. You take a sentence, hide maybe 15% of the words, and train the model to predict those hidden words based on all the surrounding words.
Ah, so it has to really learn what words mean in context.
Precisely. It builds a very rich, contextual representation of language.
Use cases for BERT.
Anything that needs deep comprehension. Text classification, like figuring out if a review is positive or negative. Named entity recognition, finding mentions of people, places, companies. Question answering, finding the exact answer phrase within a paragraph. Semantic search.
Strengths.
Yeah.
Deep understanding. Limitations.
Yeah.
Not built for generating flowing text.
You got it.
Okay, decoder for generation, GPT, encoder for understanding, BERT. What about T5?
P5, text-to-text transformer, this one uses the full encoder-decoder architecture. Its big idea, really elegant actually, is to treat every single NLP task as a text-to-text problem.
Every task. How does that work? Like for classification.
Yeah, so instead of outputting a class label, you literally train it to output the word representing the class. For translation, you'd give it input like translate English to German, the house is wonderful, and it outputs this house is wunderbar. For summarization, summarize long text, and it outputs the summary.
Huh. So you just tell it what to do in the input text.
Exactly. It provides this unified framework. It's often trained using a technique called span corruption, where it learns to fill in missing chunks of text.
Sounds super versatile.
It really is. Great for sequence-to-sequence tasks like translation, summarization, question answering where the answer needs to be generated, even classification, as we said. Strength is that unified approach. Maybe a slight downside is the full encoder-decoder can use more memory during inference than just a decoder if all you need is generation.
Okay, stepping beyond those core architectures.
Yeah.
Claude, from Anthropic.
Right. Anthropic's big focus is on AI safety and alignment, building AI that is helpful, harmless, and honest. Claude is their main model family embodying that.
And they have unique training methods for that, like constitutional AI.
Exactly. That's a key part of their approach. Instead of relying solely on human feedback to steer the model, they also train it using a set of explicit principles, a constitution, to guide its behavior and make it less likely to generate harmful or undesirable content.
So use cases lean towards safety-critical stuff.
Often, yeah. Chatbots where you need strong guarantees about behavior, content generation that needs to adhere to strict guidelines. Strength is that built-in focus on safety and alignment. They might sometimes be perceived as a bit more conservative or cautious in their responses because of it.
Makes sense. And the trauma. They've made a splash recently.
Yeah, Mistral AI, the French company. They've gained a lot of traction partly by releasing powerful models with open weights.
Meaning anyone can download and run them.
Pretty much. The model parameters are publicly available, which is great for research, transparency, and for companies who want to fine-tune and deploy models on their own infrastructure without relying on proprietary APIs. Their focus is often on efficiency, getting great performance for a given model size or compute budget.
How do they achieve that efficiency? Any specific techniques?
Well, they've released some very strong, dense models like Mistral 7B that perform exceptionally well for their size. But they've also been pioneers in popularizing mixture of experts or MoE models like their Mistral series.
Mixture of experts. What's the idea there?
Okay, so a MoE model actually contains multiple expert subnetworks within it. It might have a huge total number of parameters if you add up all the experts. But here's the clever part. For any given input token, the model only activates and uses a small subset of those experts, typically just 2.
So it has the knowledge capacity of a giant model, but the computational cost for each step is much lower, like only using the specialists you need.
Exactly. It's a way to get really high performance, comparable to much larger dense models, but with significantly less computation needed during inference time. Great for efficiency.
So good for performance per watt, basically.
Right. Popular for open research, customization, situations where you need that balance of power and efficiency. The trade-off, maybe, is that deploying and running MoE models efficiently can be a bit more complex because you need that routing mechanism to select the right experts for each token.
Wow. Okay. That's quite a tour of the major players. So if you're listening and thinking, okay, I want to actually use one of these, what are the really practical things you need to nail down first?
Yeah, good question. Choosing the right model is absolutely step one. And it starts with your task. Really ask, am I primarily generating text or understanding it? That's your first big filter decoder only, encoder only, or maybe encoder decoder.
And then comes data and resources, I assume.
Totally critical. Do you have the right data? And crucially, do you have the compute budget? Pre-training one of these giant from scratch, forget it unless you have nation-state level resources.
So for most people, it's fine-tuning.
Almost always. You start with a powerful pre-trained model, like one of the open-weight Mistral models, or maybe a foundation model via an API, and then you adapt it to your specific task or domain using your own much smaller data set. It's vastly cheaper and faster.
But sometimes maybe you don't even need to fine-tune, just talk to it the right way.
Exactly. Especially with the biggest, most capable models, prompt engineering can get you surprisingly far. Crafting clever prompts, giving it examples within the prompt itself, few-shot learning can sometimes be enough, especially for tasks that are somewhat general.
But if you needed to know really specific stuff,
then fine-tuning is usually the way to go. Or maybe techniques like ARGEN, retrieval augmented generation, where you give the model access to external documents. There are also parameter-efficient fine-tuning methods like LoRa, which are a nice middle ground adapting the model without retraining everything.
And data prep. Still king.
Always. Garbage in, garbage out, maybe even more so with these models. You need clean, relevant, high-quality data. That means careful cleaning, dealing with duplicates, and proper tokenization, breaking the text into the pieces the model actually understands. And if you're fine-tuning, the quality of your task-specific labels is absolutely critical.
Then there's the hardware. Can't run these on a laptop usually.
No, not the big ones anyway. Infrastructure is key. You need GPUs, often lots of them, for efficient training and even for fast inference. You need to think about RAM, storage. These models and data sets are huge.
And serving them, making them available.
Yeah, deployment needs planning. How will you serve requests? How will you scale if you get lots of users? Maybe you'll use quantization to shrink the model and make it run faster. Maybe you need model parallelism to split a huge model across multiple GPUs. MOE models add their own serving complexity with the expert routing.
And how do you know if it's actually working well and stays working well?
Right. Evaluation and monitoring. It's not a one-time thing. During development, you use metrics like BLEU for translation, Rouget for summaries, F1 for classification, maybe perplexity to measure general language modeling ability, FID for images.
But numbers aren't everything.
Definitely not, especially for generation. Human evaluation is often essential. You need people to actually read the output and judge its quality, coherence, helpfulness, accuracy.
And once it's live,
continuous monitoring is non-negotiable. Track the basics, latency, error rates, but crucially, track the quality of the outputs over time. Is it starting to hallucinate more? Is its performance degrading on certain topics? Are there safety concerns popping up? You need logging, sampling for human review, maybe automated checks, and a feedback loop to catch problems and retrain or update as needed. It's a living system.
Okay, let's nail this down with an example. Say you want to build a system to answer questions about your company's internal tech manuals. Walk us through it.
Okay, good practical example. Goal. Employees ask questions, get answers from the docs.
Step 1.
Data, gather all those manuals.
Yeah.
Extract the text, might need OCR if they're scanned PDFs, clean it up, and importantly, break it down into manageable chunks, maybe paragraphs or sections.
Then pick a model.
Yep, model selection. You've got options. You could fine-tune a T5-style encoder-decoder. You'd train it to take the question plus a relevant chunk of text and generate the answer. Or a two-stage approach. Use a BERT-style model as a retriever, train it to find the best text chunks from all the manuals that match the question, then feed the question and those chunks to another BERT-style reader model trained to extract the precise answer span from the text.
Let's stick with the T5 idea for now, fine-tuning it.
Okay, so fine-tuning. You need training data. That means creating question-answer pairs based on your manuals. Maybe you generate these semi-automatically. Maybe humans create them. You feed these pairs into your pre-trained T5 model and train it for a while, adjusting learning rates, batch sizes, etc. You'd evaluate it on a separate set of QA pairs using metrics like F1 score or exact match.
Got it. Models trained. How do people use it?
Deployment. You package the fine-tuned model, maybe using a tool like TorchServe or TF Serving. You deploy it, probably behind an API. You might quantize it first to speed up inference. You set up the infrastructure to handle requests. So an employee sends a question.
Your system maybe first finds the relevant text chunks.
Right. You might still need a retrieval step even with T5 if you have tons of documents. Then it passes the question and the best chunks to the fine-tuned T5 model.
Yeah, and gets the answer back.
And returns the generated answer to the employee.
Final piece, keeping it reliable.
Absolutely crucial. Monitoring and feedback. Log everything, questions, answers, maybe confidence scores. Have humans periodically review sample answers for accuracy, especially on tricky or frequent questions. When manuals get updated, you need a process to incorporate that new info, maybe rechunk, create new QA pairs, and refine-tune. Watch for quality drift, errors, latency spikes, collect feedback from users. It's a continuous cycle.
Wow. Okay, that really connects the dots.
Sure.
From a single neuron learning all the way to building and maintaining a practical QA system using these massive models.
Yeah, it's quite the journey. We went from the basics of neural nets learning through backpropagation.
To those early generative ideas, the autoencoders compressing and VAEs smoothing things out, and the GANs with their adversarial game.
Then the transformer revolution with parallel self-attention, enabling these huge models.
And we unpack the big families. GPT for generation, BERT for understanding, T5 doing text-to-text for everything, plus Claude's safety focus and Mistral's efficiency and openness.
And finally, yeah, those practical steps. Choosing models, fine-tuning versus prompting, the critical role of data, infrastructure, and that ongoing monitoring.
It feels like we've definitely built up a solid technical map here. More than just the buzzwords, you get a sense of the mechanics.
And that ability to create, not just analyze, is the really transformative part, isn't it?
Absolutely. So maybe a final thought for people to chew on.
Well, think about the sheer scale. These models have processed text, code, sometimes images, representing a huge chunk of human knowledge and creativity. They find patterns we'd never spot, so as they get even better, more integrated, what new kinds of creativity could emerge? What scientific breakthroughs might they accelerate? What problems could we solve by collaborating with these generative systems?
Finding patterns across domains.
Yeah. The potential seems immense. But of course, it also brings massive questions about responsible development, bias, impact on jobs, misinformation, how we steer this incredibly powerful technology. Lots to think about.
Definitely. Keep learning, keep exploring.